So today's lesson is going to be on graphing rational functions, and we're going to focus on finding holes in the graph and vertical asymptotes. We're going to go over what those two things are within this lesson, but just to kind of regroup, we just finished our unit on simplifying and solving rationals, and this is now the extension. We're going to look at what these graphs look like. So a rational function is a quotient of polynomials. So it's a quotient of polynomials, but it is a function. So that means when we graph it, we have, it passes the vertical line test, so it's a function. And then also we know that the denominator cannot equal 0. So just to go through some goals of the lesson, here's an example of a rational function. Okay, that's what it will end up looking like, many of these. Rational functions can look like a variety of different ways. However, we're going to primarily look at ones that look like this for the time being. And then we'll explore some other ones that have very different characteristics. So first, what we're going to do today, we're going to find any holes in the graph. And then we're going to find vertical asymptotes, and we're going to go over what those are. And then x-intercepts, which we know how to find, and y-intercepts that we know how to find. And then tomorrow or next lesson, we're going to go through what horizontal asymptotes are. So before we end up graphing these by hand, we're going to start off by finding these key items so that we can graph them. So just looking at this photo, this picture of the graph, we have this vertical dashed line. This is a vertical asymptote. I'm going to abbreviate as VA. And this is a vertical asymptote, and then going horizontally, this dashed line is a horizontal asymptote. So we have a vertical asymptote at the line y or x equals 2, and we have a horizontal asymptote at y equals 1. So these asymptotes are lines, and they are lines that a graph will approach and get very, very close to, but it will never touch. So that's the definition of a vertical asymptote. I'm going to give us a minute to write it down in a second on the next few slides. A horizontal asymptote have different characteristics, and we're going to talk about those next class. So we'll really focus on finding vertical asymptotes today. X-intercepts. Notice here how we have an x-intercept. That is a point in which the graph is going to go through. And then at 3, 2, we have a hole in the graph. And a hole in the graph is an open circle. So similar to piecewise functions, when we had open circles in the graph, we can have holes in the graph for rational functions. So the main difference between graphs of rational functions and polynomial functions. So remember our last unit, polynomial functions, we had graphs that looked like this. We had the U. But notice how polynomial functions, we did not have to pick up our pencil. However, for rational functions, we do have to pick up our pencil. So rational functions are discontinuous and have asymptotes and holes. And then polynomials are continuous. So the asymptotes and holes are points or are domain restrictions. So a rational function has domain restrictions, whereas polynomial functions do not. Okay, so let's look at the parent function for a rational. And we're going to begin by graphing f of x equals 1 over x. And so if I'm asking you what the domain restriction is, I'm asking you what can x not equal? X cannot equal 0. Because if we had 0 in that denominator, that it would be considered undefined. So let's look at this graph, or we're going to create a t-chart and we're going to choose some points. So if x is 0, we know that's undefined. If x is 1, and we have 1 over 1, it's 1. If x is negative 1, we have 1. If x was 2, it would be 1/2. If x was negative 2, we'd have negative 1/2. If x was, what if x was 1/2? So let me do that work over here. we have f of 1/2. We have a complex fraction over here, so we can multiply by 2. So f of 1/2 is positive 2. And then f of negative 1/2 is negative 2. So let's look and see what happens on this graph. So we have x is 0 is undefined. So we have points 1, 1. We have points -1, sorry, -1, -1, excuse me, I miswrote there. And then at 2, 1/2. And then at 1/2, we're going up to 2. So at -2, we have 1/2, and -1/2, we have -2. So we have this shape of a graph, and notice how if we connected the dots and we kept choosing point values for x, this would get closer and closer to 0. So I could plug in 1,000 for x. So that means all the way that way at 1,000, we have 1/1,000th that's on the graph. So it's very close to 0, but it's not quite touching. So we have things called asymptotes, and that's why these are shown. So we have a vertical asymptote at 0, and notice how we're getting closer and closer to the x-axis, and we'll have a horizontal asymptote. So notice how the degree of the numerator is different from the degree of the denominator here. So we're going to come back to this and review why the degree, or how that degree of the numerator and denominator help us with the graph. So this is a different graph. We haven't seen a graph like this before, but we could definitely graph. So domain restrictions for rational functions can either be a hole in the graph or a vertical asymptote. So those are the two domain restrictions. So let's focus on these two today. So a hole in the graph is a point of discontinuity. It is shown by an open circle in the graph. And not all rational functions have holes. So they can have holes in the graph, but they don't always have holes in the graph. So now to find a hole, we want to factor the numerator and denominator. So we're going to use this particular example of x below. So we're going to factor the numerator and denominator, and I can factor the numerator into x plus 2 times x plus 1, and then we have x plus 1. And if I asked you in our previous unit to simplify, we would all say we're going to reduce the x plus 1s and be left with x plus 2. So when we have a common factor on the numerator and denominator, this represents a hole in the graph. So we know there is a hole where x equals -1. Okay, so we're going to solve it in the same way that we found roots. So if we plugged in -1 into this function, -1 plus 1, that's 0. Remember, that's a domain restriction, which is a hole. Okay, so now we know on the graph we have a hole at -1, but we don't know where the hole is located. So if I had a graph, at -1 is here, I don't know where the hole is located. Is the hole located up that way, above the x-axis? Is it located below it? Is it here? So we need to know where to place this point on the graph so that we know that key point. So how we find a hole in the graph, how we find the coordinate point of the hole, the coordinate point or the y value of the hole. So what we end up doing is reducing this function. So the reduced function is x plus 2. And what we end up doing is plugging in -1 for the reduced function, and we get an output of 1. So we know that the location or the coordinate point is at -1, 1. So this is a bit tricky, so this is something that we're going to be practicing over the next week. Okay, so vertical asymptotes. A vertical asymptote is a vertical line that a graph approaches but never crosses. So this is key. The vertical asymptote is a line in which the graph will never cross. So now to find a vertical asymptote, we're going to factor the numerator and denominator. So that top we're not factored yet. So we have x, and then the denominator we have x plus 2 and then x plus 3. So remember, a vertical asymptote is a domain restriction. So notice how there's no hole in the graph, right? That we don't have any common factors. So that means we could have two vertical asymptotes. So we can have a vertical asymptote at x equals -2 and a vertical asymptote at x equals -3. So we're always going to express a vertical asymptote as an equation of a line. Again, a vertical asymptote is a domain restriction, so that's why we're looking at our denominators. Okay, so let's put this all together. We want to find any holes in vertical asymptotes in the graph, and then we're going to talk about how to find x-intercepts and y-intercepts. So our first thing that we do is always to factor. And then our denominator, we have x plus 3, x minus 1. And what do you notice? Notice how we have a common factor in the numerator and denominator. So that means we have a hole where x equals -3. So once we reduce that hole, we can now find the coordinate point. So our new function is x squared over x minus 1. So when we plug in -3 for x, we get 9 over -4. So we have a hole at -3 comma -9/4. Okay. So now that we found that domain restriction, notice how there's a remaining factor in the denominator. So this represents our vertical asymptote. So we know we have a vertical asymptote at x equals 1. And now to find x-intercepts. So to find an x-intercept, we find the reduced function, okay, so this same function, and we're going to set the numerator of the reduced function equal to 0. So remember, to find an x-intercept, we set y equal to 0 and then solve. So if we have f of x in our reduced function is x squared over x minus 1, we now want to do 0 equals x squared over x minus 1. But look what happens when we multiply both sides by x minus 1. We get 0 equals x squared. So x equals 0. So if I have a y-intercept at 0, 0, then that also means I have, or sorry, if I have an x-intercept at 0, 0, that's the origin. So that is also my y-intercept. So we're still using the same strategies to find x and y intercepts. So to find x-intercepts, we're going to set the reduced numerator equal to 0 and solve. And you cannot have a hole and x-intercept at the same point, which is why we need to use the reduced function. To find the y-intercept, we're setting x equal to 0, or we'll find f of 0 to solve. But if you have an x-intercept at 0, 0, then this is also your y-intercept. So that's just a kind of like a way that we can jump to that answer. Okay, so let's finish up with this problem here. So we want to find holes and vertical asymptotes. So we first have to factor everything. So our numerator and our denominator. Notice how we have a common factor in our numerator and denominator. So we have a hole at where x equals -4. So the reduced function is x minus 3 over x plus 5. And we'll plug in -4 into the reduced function. We have -7 over 1, so -7. So we have a hole located at -4, comma, -7. So when we begin graphing, we're going to know where that is listed. So now the vertical asymptote, again, it's the remaining factor after you found your hole. X equals -5, that's the vertical asymptote. And then the x-intercept, notice how the reduced function is only left with x minus 3 in that numerator. So the x-intercept is 3, comma 0. And then the y-intercept, if we set x equal to 0, notice how we have these constants here. So we have 12 20ths. So if we divide by 2, or 4 rather, we get 3/5. So we know at 0, 3/5, we have our y-intercept. So in the same way we found our y-intercept for quadratics, we're going to find the y-intercept if we have constants here in this rational. So those are all the key points. So for homework, you're going to complete a worksheet, and from there you're going to practice going through and finding holes, vertical asymptotes, and x and y intercepts, and we'll begin graphing next class.